Hello, GopherCon, and welcome to How Apache Beam Makes Your Data Processing Go. I'm Robert Burke. Despite my tongue-in-cheek self-insert title of Distributed Gopher Wrangler, I'm a senior software engineer at Google, working on Cloud Dataflow. I've been working on the Apache Beam Go SDK for about 4 to 5 years now, so hopefully I know what I'm talking about by now. And I've been playing with Go since around V1, which is 20, I almost did it. 2009, not 2019. But it's been lovely to see how it's grown over that time. In case you haven't seen me around the conference yet, I'm the one with the combination of a mustache and matching glasses and fun hair. Come say hi. So, in this talk, I'm going to cover a quick overview of what Apache Beam is, and from there we'll get into the go of it, with how the SDK uses reflection, interfaces, and generics to execute your code, which we call dofunds. Importantly, for those of you watching the video later, this talk doesn't cover how to use Apache Beam, or anything really specific about the Go model, or the Beam model. For that, the Beam programming guide and quick sites on the Apache Beam website are the best resources. I'll be linking this slide deck in the GopherCon Discord and from my Twitter after the talk is done, so you'll have a lot of links to resources to look at afterwards there. The speaker notes also have links to the various code snippets that I'll be showing screenshots of. So, since this is the first time in a long time with like a big live audience, quick audience poll. Everybody raise your hand up, please. Yeah, just one hand at all. If you've heard, keep your hand up if you've heard of Beam before this talk. Okay, that's pretty good. Keep your hand up if you've used Beam at all. Okay. Small handful left. And keep your hand up if you've used the Beam Go SDK specifically. Dang it. Well, hopefully we'll change that after a few of these kinds of talks. Otherwise, I'm the only one who can answer questions, and that's not great. So, for everyone, what is Apache Beam? Beam is a portable model. It's not a specific language SDK or runner project. It's a way to do your data processing in a language that's familiar to you, on top of infra you're already using. It's a way to divide the complexities of data processing between the runners and the user SDKs. And not just to be able to reuse pipelines on different runners as your infrastructure changes, but also to be able to portably reuse transforms from other SDKs in the SDK language you're already comfortable with. We call that cross-language. Beam is also a unified model. Beam resolves a tension between batch processing and stream processing, especially when stream processing is trading off between correctness and low latency results. It's a way of thinking about how to process your data so you can reuse the same transforms in both modes. And the Beam vision is that it wants to support end users who are just interested in writing data pipelines. They want to use the language they want to use and choose the runtime that works for them, whether it's something on-prem or a hand-tuned cloud cluster or in a fully managed service. In addition, we want to develop stable APIs and documentation to allow others in the open source community to create Beam SDKs in other languages and to provide runners for alternate distributed processing environments. Currently, we have a number of languages that implement the Beam model. So we've got SDKs in Java, Python, Go. We have an adaptation for SQL, and also, since January, an experimental TypeScript SDK. And then we have a list of runners as long as my arm. So, that's the 10,000 feet view of Beam. Let's get to how Beam works. There are a lot of problems for a Beam SDK to resolve, but I bring it down to these kind of two core problems when you're developing an SDK. One, how to have an API that feels good to experienced users of the language, and 2, how to actually execute that code. So, how do we begin to do that with Go? The apocryphal story of Go, and this audience probably has heard all of this before, but is that it was originally conceived of during a long C++ compilation. The Go authors took this as a sign that programming could be faster, and they focused on making a new language that's easier to read, easier to write, compiles quickly, and executes quickly. This ethos drove the design of the language, leading to one that's strongly typed, statically compiled, avoids inheritance and overloading. On top of that, it brings concurrency into the language itself, instead of leaving it off to libraries. It also has a standard library that is useful for the internet age. As one of the keynotes mentioned, it's very well suited to distributed computing. None of these ideas are new, but they had not come together in this way before. But others seem to agree, and it's become a language upon which the cloud has been built, and powering things like Docker, Kubernetes, to name just 2. Until recently, Go didn't have generics, which affected a lot of implementations of things in the language, including the Beam SDK. So we'll see how that develops over time. But like any programming language, Go's features and affordances affect how people design the APIs and resulting SDKs. And that directly affects your user experience, from the initial authoring to how to deploy it to production. So for Beam, an SDK is an implementation of the Beam's abstract model. A simple interpretation of this is how users express the p-transforms, the manipulations you want to do with your data, and to the actual collections of data in a pipeline. The SDK is there to make sure that everything makes sense, and that it can execute your do funds, as we can call them, at pipeline execution time, while catching potential runtime errors earlier at pipeline construction time. So let's see how that kind of looks for Go. There's 3 steps that we're going to really kind of go over a little bit here. 1, we construct a pipeline DAG with do funds, that is your code, and other transforms. The pipeline uses deferred execution, so until it's submitted to a runner, and is thus serialized and processed, it's not actually being executed. You're configuring the computation. The runner then decides how to execute the pipeline, and where, whether that's locally or some remote VM. This is what a pipeline construction looks like, with a bit of additional formatting for the sake of the slide. As promised, this isn't going to actually teach you Beam technique. It's to illustrate what a pipeline looks like. Lightly, we have transforms, which are all the function calls on the right side. And then we pass around the resulting p collections, all the variables defined on the left side. The second parameter on each of the pardo calls are in bold. These are the pipeline do funds. These are the code that you want to execute your data on. So the big problem we run into, though, is the do fund types. So this is a type signature for a do fund. So is this. Do funds aren't only just functions like the extract country info fund there, they're also arbitrary structs with process element methods. And it goes on with different types for each of these sorts of things. The observant among you will see that none of these types actually match up. So interfaces or vanilla function types are kind of right out. We can't define an interface for process element, nor can we define an abstract version of a function, func type signature, to match with all of these. But we need to be able to call and execute all of them. We could have gone with an approach that just used the empty interface, but that would, any, I guess, now. After all, it's easy to do everything with interfaces in Go. But that approach loses information and could require too much repetition elsewhere. So we kept the user types, and this brings dofuns closer to normal Go code. After all, static types are a valuable Go feature. Invariably, this sort of thing requires use of the reflect package. Reflect has a function. It's got many functions, but right now we're talking about type of, which gets the type of any value you pass to it. From there, we can do a bit of work to make sure that the pipeline is type safe at pipeline construction time. Whenever you write reflection-based code, you get used to writing switches. So we take the function or method type, if it's a structural dofun, and look through its parameters. This tells us a lot about how the dofun processes its elements. All dofuns have a main input type, and we need that to make sure that the pipeline works and is consistent when we construct it. But then there's all the rest. Most of these things the framework will generate for you, but in the end we want you to use your own types for your data. You know your data best, after all. This move is by using your actual types, this moves a class of error from pipeline execution time, if we were using just interfaces and forcing everyone to use type assertion, to pipeline construction time, and avoids a costly error that could happen at the end of a multi-day pipeline, because the types didn't match up in some esoteric bit of code at the end of the run. So, how can we call all of these, then? Well, reflection rides again. Reflection doesn't just let your code introspect types, it also lets you look at and write metacode about the values, too. The reflect package has a function, value of, which produces a reflect.value. And one of the many methods on reflect.value is call. If the value isn't a func or a method, it panics. But ultimately, call ends up taking its parameters and calling its function value. Okay, so we have a way of executing these functions. It's in the standard library, that's pretty good. How does it perform, though? So, to get a comparison, we wrote some micro benchmarks for how we're calling structural dofuns, their process element method. To get a clear overhead measurement, we need a baseline. So here's calling the method directly. On my Chromebook here, it takes about 7 nanoseconds per call. Not bad. This is the minimum Go's compiler will allow us to go for now, at least on my machine right here. This is pretty great. Now that's function call overhead for you. The method I'm using for all of these, by the way, is simply just adding one, or like a fixed constant, to a number, so not a lot of work is being done there. Well, let's see how reflection goes. Ugh. 519 nanoseconds per call, and a bunch of allocations. For those of you able to do the quick math, that's about 75 times slower. Now, this was a pretty naive implementation, but we felt we could do better. But in order to make it better, first, we need to make it worse. we need to add some indirection. In this case, we decided to indirect through interfaces, and specifically slices of interfaces. You'll note that our call method at the bottom there is very similar to reflect.values call method, but instead of slices of reflect.values, it uses a slice of interfaces. The value of function, that's the most deeply nested bit there on line 87, simply converts a slice of interfaces and calls value of on them, converting them to reflect.values. Interfaces, right beside the return there, does the reverse, converting a slice of values into a slice of interface. So, how much worse is this? Just under twice as bad as the vanilla call, but 143 times worse than our baseline. So why did we do this then? Why go through interfaces if it's just going to add a lot more overhead that way? Because interfaces let us use type assertions. Type assertions are very fast and well optimized by the compiler, but they require writing specific types at coding time so the compiler can assist. You could write these by hand, but we're programmers, so we automate it instead. So in the earlier days of Beam Go, we used code generation to assist to automate making these kinds of caller shims. With a bit of static analysis, I wrote a tool that would look at your do funds and pick out the types, and then generate something like a reflective caller. The code ended up looking like this for all the generated code. And if users wanted to, they could run the generator on their own do funds like we did with Go Generate. So this example comes from the Beam Go stats package. So it's got a very similar but not identical functions. If you look at the list of identifiers on the Go Generate line, this specific caller is for functions that take in two float 64s and return a single float 64. Also included on line 135 there is a factory function that takes in an interface, type asserts to the expected function type, so func, float, float, return func, or return float 64, and then ends up returning the interface we call reflectx.func. The type itself has a single field, the function that it's wrapping. It has the same name, type, and call methods, so that it implements that internal func interface. At the bottom there's even a call 2x1 method, so it can avoid slice allocation whenever we know the arity of the function we're calling, for an entirely different set of interfaces. You'll note that either call method simply type asserts that the values passed in are going to be float 64s, and then calls the function normally. So I'm going to move on from the code generator, though, because it's the code generator, despite solving the problem we were having with the expense of reflect, is kind of hard to use. It's buggy. It's hard to replicate the full breadth and depth of the Go type system when you're just always running through static analysis. It's hard to cover all those edge cases. Oh, how delighted I would have been if we had fuzzing back then. And the hard part, for sure, is making sure that users remember to actually use it, because it required running something like Go Generate in order to do it. We use this a whole lot internally to Google for with the SDK, of course, but we could get around it because we have a lot of excessive tooling around our build system. which allowed me to set up some Bazel build rules effectively that called the code generator. So we needed something better. And in Go 118, I'm not sure if you know this, but something big happened. Generics came to Go. And generics are a big deal for something like this. The code we had there is very boilerplate heavy. It doesn't actually do anything with the types other than use them for type assertions. So the values are merely just passed around. We don't actually care what the types are, just that they are the right types that we expect. And aside from me not wanting to show you the terrible manual template code I wrote for the static analyzer to sub stuff into, the generic version is just easier to read anyways, because people are getting used to how to read generic Go. Isn't that right? So this is the generic version of the same. It's got the same scaffolding as before. This is the generic caller for a function that takes in 2 parameters and returns a single parameter. If you look at the call method, we type assert into our generic parameters and call the function as before. Easy peasy. And best yet, we could write a code generator to generate this. So how does it perform? 87 nanoseconds. A dramatic improvement. While it's still over 12 times slower than the native Go code, this is the overhead for each call to the function. The lesson here is to amortize it. Write do funds that do work. And you won't notice those extra 80 nanoseconds that it takes to invoke the function. So how do we've got this way of executing the do funds, arbitrary do funds. So how do we actually make use of any of this? That much is pretty easy. We register them and then look them up at runtime. The registration looks pretty straightforward like this at this point. We have this package called register, which has all the generic registration functions for Beam. Functional do funds are simple enough that the compiler can infer the types of them appropriately. So we didn't even need to add the specific parametric type parameters to the function at call time. Functional do fund or structural do funds with the process element method have additional methods as well that I have not mentioned in this talk that we need to check and make sure they match with the process element method. And this complication ends up requiring that the generic function has manually specified types. That's the cost of additional do fund configuration, I guess. But who knows? Maybe in some future version of Go, in type inference will allow us to simply pass the parameter in and not have to manually get everything correct. But at the very least, the compiler will make sure that all the types match up. This kind of registration must be done before the Beam init call, which happens before pipeline construction. This way, it makes it, the Beam init call is something that splits off your binary from being in either pipeline construction mode or pipeline execution mode. So if you want your code and the advantages of the system to be ready, it needs to be available to both. I recommend putting this kind of code in an init block, where it's available to the system and the workers. Again, the small cost here is that because you're calling a bunch of functions and making sure they're living in a map, this prevents the compiler from doing a little bit of pruning at the linking stage. So, a little bit fatter binaries, but it's significantly smaller than anything Java or Python comes up with, so I'm pretty happy with it. To serialize things at pipeline construction time. We have through the reflect package, we have the fully qualified names for the types and functions, which allows us to key off them for lookup in our generated factories. Those are registered by these helper functions too. So, you may be asking, how much of a difference does this make? I know I've mentioned that it reduces the overhead, and I've shown some benchmark numbers that I've called pure overhead. But despite despite the way the slide deck may appear, I'm a much more visual person. It's just when you're talking code, you can only write so much and do so many pretty diagrams. To make this the end of this talk a little bit more interesting, I ran a load test of a pipeline on a Google Cloud Dataflow with and without the caller adapters. And since I used the upcoming 2.4.2 version of the Beam Go SDK, I was able to collect some profiles with Cloud Profiler as well. So the load test pipeline I used just sets a random seed and then passes random byte slices through a line of do funds. In this case, something called counter operation fun. To use the old reflect way, you only need to use the soon-to-be-deprecated beam register type or beam register function methods to make sure that the system knows where they are. The Cloud Profiler, fortunately, color codes packages pretty nicely. So in this case, that little sliver of gold, which, let's see here, that little sliver of gold off to the bottom left side, there is the counter operation function, and then all of that green is reflection overhead or runtime overhead. So, as you can see, it takes up a sizable amount of the profiled time in the pipeline. So now compare to when we register things and use the generic caller methods that use type assertion. Look at that. Look at how much space random generation now takes up, and then and all of that green, that is simply the runtime conversion from byte slices to interfaces. And it's very clear where the counter operation function call is. And since I ran this on Dataflow too, it's reasonably easy to see how much resources we took up. But it's a pretty static load test. The load test itself pins things to 5 workers because we're trying to measure throughput and then get a comparison between the SDKs. At the tops, you can see the run times between the two. And as you can see over here, it takes about half the time, 12 minutes versus 24, to execute the pipeline with the lower overhead of the type assertion callers. And it matches up that it takes about half the CPU. So that's pretty good. If you'd like a demo of Dataflow and using the Beam SDK, come find me tomorrow somewhere at the Google booth. I'd be happy to show you around. So what's next for where performance is going for Beam Go? Because we now have all these generic registration functions, we have access to the types and the actual functions fairly directly. So that gives us a lot of information about the do funds. So we can specialize our execution further and possibly get rid of other chunks of the framework overhead that is only loosely being showed by this small snippet of a profile. This combined with future compiler optimizations with profile-guided optimization we should see further reduced overhead. So I'm very excited and following that GitHub issue very closely. And if you'd like to learn more about Beam and the Go SDK, I'll link this slide in my Discord channel, or in my channel in the Discord, and tweet it from my Twitter as well. It's got links to a bunch of previous talks of mine, which talk about different facets of Beam or the SDK, and to a bunch of shared Beam resources. I hope you find them useful. I have been Robert Burke, and this has been How Apache Beam Makes Your Data Processing Go. Thank you for listening, GopherCon.